Hello everybody, my name is Hans Bodlaender and I will give a lecture on parameterized complexity of bandwidth of caterpillars and weighted path emulation. In this talk I'll first discuss what is the bandwidth problem, then I'll give some history of the complexity of the problem, both the classic version and the parameterized version. In this talk we'll show hardness proofs for the parameterized version of bandwidth, and as an intermediate step we show a problem called uniform weighted path emulation to be hard for all classes WT, for all integers t, and then show the hardness of bandwidth. In the end I'll tell about a new development and show that the problem is actually XNLP complete, and I'll end the talk with some conclusions. So what is the bandwidth problem? We are given an undirected graph with n vertices and some integer k, and we want to number the vertices from 1 to n, so find the bijection from the vertices to the numbers 1 to n, such that for every edge, the difference between the numbers of the endpoints of the edge is at most k. So you see an example here on the slide where we number the vertices from 1 to 8, and for every edge, the difference between the two numbers of the endpoints is at most 3. So this is a layout of bandwidth 3. And we want to find for a graph numbering where the total difference is at most k. So this problem is equivalent to a problem about matrices where we have a symmetric matrix and we want to simultaneously permute the rows and columns of this matrix such that all the non-zero entries are like a band of width at most k along the main diagonal. And for this reason, this has an application for Gauss illumination. The bandwidth problem has been studied very often and already for a very long time. So already in 1976, Papadimitriou showed that this problem is NP complete. But the problem is actually NP complete for very special classes of graphs. And in 1986, Monin showed this problem is NP complete for a kind of trees which are caterpillars with hair length at most 3. And later I'll tell you what this class is. If you have a caterpillar where the hairs have length at most 2, then the problem is actually polynomial time solvable, which was shown by Assmann et al. In 1981. The parameterized version is known for a long time to belong to the class XP. In 1980, Sachse showed that this problem can be solved in n to the k plus 1 time, which was later improved by Gurari and Sudbury to n to the k time. In 1994, Mike Fellows, Mike Hallett and I wrote a paper where, among other results, we claim that the bandwidth problem is hard for all the classes WT, for all integers t, even if the input is a 3. But the proof was not written down for many years. And this paper is the first time that we actually write down this proof of this claim for a slightly more restricted class of trees. Also, in the 1990s, Mike Hallett conjectured that bandwidth actually does not belong to the class WP. In 2014, Draghi and Loksanov showed that bandwidth is W1 hard for trees with hedge path width 2, and they also show that there is no n to the little o of k algorithm for bandwidth assuming the exponential time hypothesis. So now let's tell what is a caterpillar. A caterpillar is a special type of tree where we take one path and then attach to that path a number of other paths. So these other parts I call hairs. And you can see an example here. We have a caterpillar where the hairs have length at most 3. Another way of stating that is that you have a tree where all the vertices with degree more than 2 are on one path in the tree. So our main result is that bandwidth for caterpillars with hair length at most 3 is WT hard for all the classes WT, for all integers t. And we show this in 2 steps. We first go to an intermediate problem called uniform weighted path emulation and prove hardness starting from weighted t normalized satisfiability. And then from the uniform weighted path emulation, we go to bandwidth. So what is weighted t normalized satisfiability? We are given a Boolean formula, which is a conjunction of a disjunction of a conjunction of a disjunction, etc., where we have t levels. So we have t levels where we alternatingly have ors and ands. And the normalized in the name of the problem tells us that each of these terms, each of these conjunctions and disjunctions actually has the same number of terms. Also, we're given an integer k, which is the parameter, and we ask whether we can satisfy this formula by setting exactly k of the variables to true and all others to false. In 1992, Downey and Fellows showed that this problem, weighted t-normalized satisfiability, is complete for the class Wt. And this is the starting point of our reductions. We go from this problem to uniform weighted path emulation, which is a weighted variant of a problem called uniform emulation, which was introduced in 1982 by Fishburne and Finkel for the simulation of processor networks. And later it was studied by me in my PhD thesis, supervised by Jan van Leeuwen. Here, what is an emulation of a path to another path? We have a path and we map the vertices of the larger path to the vertices of the smaller paths in such a way that neighboring vertices are either mapped to the same vertex or they are mapped to neighboring vertices. And you can see below an emulation of a path with 11 vertices on a path with 5 vertices. Now all these vertices have weight, and we say that the emulation is uniform if for every vertex on the smaller path, the total weight of all vertices mapped to that vertex is always the same. So here we see an emulation where every vertex has a weight mapped of 5 mapped to it, and we say that this is a uniform emulation with emulation factor 5. So the problem is, given these two paths and the weights, is there a uniform emulation of the larger path on the smaller path? So I'll just sketch the main ideas of the proof of the hardness. This proof has a number of elements. We have consecutively on my larger path, we have first a number of vertices, which we call the floor, which have different amounts of weights left. They make sure that the amount of weights which are left on different spots differs. Then we have k parts, which model the selection of a variable that is set to true. Then we have a number of parts which model the selection of a satisfied term of a disjunction. And in the end, we have a so-called filler path, which is used to fill up remaining weights left. And in the proof, a typical trick is to work with different types of weights, where some are large, and even larger, all a function of k and t. And in this way, we make sure that certain vertices only can fit at certain spots. So the floor has m vertices, where each of these m vertices has a weight which is larger than c divided by 2. And because of that, we cannot fit 2 vertices on the same spot. So this first part has to be mapped 1-to-1 to the path as shown in the picture. And by taking these floor vertices with different weights, we can make sure that the amount of weight left is different at different vertices, and in this way we can make sure that some vertices fit somewhere and some others don't fit somewhere. This is, for instance, used for the trick of turning, where we have some very heavy vertices which only fit at the last vertex at point M, and some relatively high heavy vertices, which we call left turning points, which only fit at vertex 1. And this forces that the path goes from 1 to M, then goes back to 1, then goes to M, and so on. Maybe doing a little zigzagging in between, but the main turns are like shown in the picture. We have k parts, each for one true variable, which we call the variable selection parts. And for this, we have a path going from the left turning point to the right turning point, where we first have n vertices of weight 1, where n is the number of variables from our formula. Then we have m vertices with large weights, actually of 2 types, and then again n vertices of weight 1. And the only way you can map this is you can start at 1, zigzag maybe a little bit, then start the heavy part at some I between 1 and n. And if you start at point I, then this model setting xi to true. And then I have this heavy part, but we cannot fold this heavy part. Then we zigzag a little bit and we end again at m. And in this way, we model which variable is set to true. And by taking some slightly heavier vertices, help for the, in combination with the other gadgets, to check if a variable is true or false for these other gadgets. The main other gadget is the disjunction part, where we have for every level of the disjunction, which is basically r divided by 2, we have a part. And for each disjunction in this level, I have a subpart. And it looks a little bit like in the picture here. So in this floor part, we have alpha vertices dedicated to each term of a disjunction. And between these parts dedicated to the disjunction, we have also alpha vertices which are empty. And now this disjunction part has 3 alpha vertices of high weight, again such high weight that we cannot fold this part, we have to map it consecutively. And these 3 alpha vertices, we must cover at least one of these terms exactly. And that term which you cover then is the satisfied term of the disjunction. So this is, with a lot of hand waving, the main idea how you actually model that in a disjunction one of the terms is true. The last part of the construction is relatively simple. We end with a path of vertices all of weight 1, and the length is such that just the total weight over all vertices of the entire construction equals c times n. And now you can use this filler part to fill the remaining weights left, and so make sure that every vertex has exactly c weight mapped to it. And in this way we get the uniform emulation. So for all the details, I would refer to the full paper. And in this way, we get a parameterized transformation from the WT hard weighted T normalized satisfiability problem to uniform emulation of weighted paths. And so uniform emulation of weighted paths is WT hard for all integers T. So the second proof is to go from this emulation problem to bandwidth, and we have again a parameterized transformation from the former to the latter, where we build caterpillars with hairs at most length 3. This construction has in sequence a number of steps. First, we have something called the left block, which is just a vertex of degree 2k. Then I have something called a ground path, where some of the vertices of the path have a lot of hairs and some don't. And this creates in the construction some gaps. Then at the right of the construction, we have the turning point. And this is a construction which is without any changes copied from the NP completeness proof by Monin. We use precisely the same gadget here. And then we have a tree which represents the emulation instance. And then we have a filler path. I'll sketch some of the details a little bit more here. So we start with a vertex of degree 2k. And if you have a vertex of degree 2k, then all the neighbors must go to the k points at the left and the k points at the right to get a layout of bandwidth at most k. So this basically blocks the entire construction, and you cannot, other parts of the construction cannot pass this block. At the right side of the layout, we have the turning point gadget of Monin, and this is a gadget which has the property that you enter at some point. Here in the picture, you see this vertex VA. You enter there, you have the turning point gadget, and then you have to go back in the same direction. So basically this blocks the right side of the construction. So between the left block and the turning point, we have a path. And with help of hairs of length 1, we create gaps. So we ensure that the vertices on the ground path must have a distance k by using some counting argument. And now we have a number of vertices with hairs. And actually, you can see here in the example, we give hairs to the 3rd, the 5th, the 8th, the 10th, the 13th, the 15th, and so on, vertices on this ground path. And so then between the 1st and the 2nd, and between the 6th and the 7th, and the 11th and the 12th, there are no hairs, so there is a lot of space. But between the others, there is only little space. And you can fit some path along it, but not vertices with a lot of hairs. And in this way, we create gaps in which we can fit other things, and other parts don't have gaps and you don't can fit things there. Then we have a tree which models the weighted path, and what we do is we have for every vertex from the emulation instance, we have a vertex with a lot of hairs, basically some constant times the weight hair. So the number of hairs is proportional to the weight of the vertex you represent. And you can see this in the picture. And between these vertex hairs, we have paths of length 6. And in this way, we model then the path. And so now what happens is that this model path has to be fit into gaps. The heavy vertices only fit in gaps. And then because there are paths of length 6 between these, neighboring heavy vertices must be either in the same gap or in adjacent gaps. And this ensures that we actually have this models an emulation of the original weighted path. And the total weight of heavy vertices in gap is at most the emulation factor times this constant, which is the number of hairs I multiplied things with. And by counting precisely, you can see that this forces that if there is a solution, then actually this corresponds to a uniform emulation of the mapping. And the example gives a little bit the main idea of the construction. Now the last part of the construction is again a filler path. I end with a long path without any hairs to make sure that I have a correct number of vertices mapped in the layout between the left block and the turning point. So there are many details which I just skipped over here in this discussion, but I hope you get at least a little bit of the intuition behind the proofs. And in this way, we get a transformation from the uniform path emulation to bandwidth, and show hence that bandwidth for caterpillars with hairs at most length 3 is hard for all the classes WT for all integers T. I end the talk with telling some recent results. So recently with Carla Groenland, Jesper Nederlof and Celine Swenenhaus, we showed that several problems are actually complete for a class for which we took the name XNLP, which is the problems which you can solve with a non-deterministic algorithm where the time is basically FPT, so a function of the parameter times a polynomial, not depending on the parameter, and the space is a function of the parameter times log n. And via a sequence of reductions, we show in our paper that uniform weighted path emulation is actually complete for this class XNLP. Now, using then the reduction from our paper, which we discuss here, you can see that the reduction actually uses log n space. So for this reason, we now get that bandwidth for caterpillars with hairs length at most 3 is actually complete for this class XNLP. And this answers the question that we asked more than 25 years ago: how complex is actually parameterized bandwidth? Because now we have actually a class of problems for which bandwidth is actually complete for. So finally, some conclusions. So it's interesting to see that there's actually quite sharp distinction between easy and hard. So bandwidth is actually polynomial time solvable if you have a caterpillar with hair length at most 2 by the result of Assmann from 1981. But in the hardness proof, we only need one vertex with hairs of length 3. There's one vertex in the turning point gadget which has these long hairs, and all the other vertices have only shorter hairs. We believe that the techniques and the weighted path emulation result can possibly also be used for showing hardness from other problems. And so candidates for these are the bandwidth, if you look at trees where the maximum degree is 3, or the directed version of a bandwidth problem. So I'm given a directed acyclic graph and want to find the topological ordering of the graph where the bandwidth is at most k, or the topological bandwidth problem where we ask whether the input graph has a subdivision which has a layout of bandwidth at most k. And that's all what I wanted to tell you. Thank you for listening.